everyone. This is Celso Batalha Astro 10. And before I start anything, let me share my window with Hardy. And for that, there you go. There you go. So now you might be able to check my window now. October 12th, one of the resources I would like you to use it is flashcard. Flashcards is interesting. I mean, after you go through the PowerPoints that I have posted in there, and check and the homework, you read the book, you check the material at the end of chapter, and then you can try and see if you have a good grasp of what's going on, and then you can test yourself here. Impact creating. So you should know what that term is, and then you write the subject. Well, what the heck is that? And then, so these are materials or terms that you should be able to have an idea of what it is. I would, oh, there is no audio? Oh, I'm sorry. Thank you. Thank you. I've been talking to you and apologize because I haven't at that moment 5 minutes ago opened my window. Hey, good evening, Hardy. I know you are not listening, but I tape it in quick time, so I will upload this conversation in Moodle, and you should have that completely. But basically, I would like your attention to the flashcard. Is one of the resources. I put it in there in Moodle. Every single chapter you have one, and it's a good thing to make use of it. It's a good way to fix concepts and test yourself and quiz yourself in the subject. Um, besides using test your knowledge on chapter 6, which is not graded. So we just finished exam 1. The grades were okay. I think the class did all right. But test your knowledge. You can go there, and after you study the subject, just play around. I mean, um, the questions might be interesting. You might give you some idea on going further into the material of this chapter or each chapter, and then you can look at these terms and try to see if they make sense or not. Okay, so this series of multiple choice questions, and there are not only 10, there are several of them. I've been accumulating for quite a while and used in the past for homework. Now I leave it in there so that you can test yourself on it. Okay, so it is a good resource, and I really recommend students to make use of it. Terrestrial worlds, what are they? Um, when the solar system was formed, and this is pretty much what we studied last week, formation of solar system. So in formation of solar system, um, gravitational field or gravity at certain moment start to pull the gas in, and eventually, so I think the basic idea, if you recall well, let me go to yes, somewhere in here. So you have gas in the interstellar medium, and then gravity start to act on the gas and pull material in. Now, the problem is these clouds, these giant molecular clouds, are not devoid of interaction in the galactic disk. So they interact, and as a result of that, they have not only gravity, but they also have rotation. So because of rotation, when this gas collapse, when the gas collapse, um, there will be a tendency of material that is in a certain angle, instead of following, stay directly towards the center of mass of the system where the star is going to be residing. If they are in a certain angle, they will fall first in the horizontal plane of that rotating system. And then from there, they will migrate inward. Oops, I hate this. I hate this software because they keep doing these tricks. So now I have to start all over. So, but what I was trying to say is, uh, if you have a gas that might that might collapse towards the center of mass in a certain angle, there will be a gas in the regions outside that angle that, instead of falling directly towards the center star right there, so I can't write on top for some reason, it falls on the disk, and then from the disk they migrate towards the star. So which means this rotating system will form a circumstellar disk. Now, as the disk evolves and as more material from it falls on to the central star, so at the end you're going to have, you ended up your system, which is called premium sequence star, with a star and a disk. So out of the disk, material gas will crystallize and form planetesimals, and all these planetesimals will circle the star, and eventually you have a planetary system and the star being formed. Now move to the material of this week class. When the star forms, um, there will be a center of heat and energy in this new planetary system, or new star system, in fact. And the heat will act on the disk itself, and then as a result of it, two different types of planets will be formed. One is the so-called terrestrial planet, and terrestrial planets, they have a rocky composition. They are primarily made of silicates, carbonates, iron oxides, so they are pretty much rocky type. And there will be forming also a different type of worlds or objects. Sometimes they are called Jovians because they resemble Jupiter, Jovians, Jove, or Jupiter. But in fact, they comprise all the objects in the solar system. They are like the giant planets, the giant planets. So giant planets like the Jovian planets, they are in fact gas or liquid type, primarily gas and liquid, or they are kind of a icy, like a uh, slurpy type of planet, like Uranus or Neptune. So they are more icy than anything else. And also you have the icy chunks called comets or Kuiper belt object, and Pluto is one of it, that also orbit the solar system. So as you form the planetary system around the sun, you have two distinct types of objects. One is rocky type and another one is icy type. So this week we are concentrated, we are talking about the terrestrial worlds. And which worlds are then? Are they? So the planet Mercury, Venus, Earth, and then Mars, and also the Moon. Moon is also a terrestrial world. So there you go. So what are the main characteristics of this world? Well, they have solid surface, so you could stand on it. Probably you'd need suits, protection, because some of them are very low density, and and some of them have no atmosphere, which means you need the extra protection. But I'm sorry, I'm eating ice cream because my daughter gave it to me. Now I don't want the ice cream melting, and I'm here giving a lecture and eating ice cream. That's crazy. I'm sorry. I should offer you some ice cream if you are listening to this, Heidi. I'm sorry. Do you like ice cream? Where are you? I can see the. Oh, you are there. Rock planets up to Mars. Yes, yes. But also, terrestrial worlds, you could include the asteroids because the asteroids are rocky type as well. So, not just Mars. So, beyond Mars, you have these asteroids. In fact, Jupiter is not a rocky type object, it's more like a liquid planet, liquid hydrogen and helium. And because Jupiter is too big and too massive, astronomers suspect the gravitational field of Jupiter was responsible for preventing these planetesimals between Mars and Jupiter to form into a planet or into a object relatively larger. But if all these planetesimals are add up, those in between Mars and Jupiter, they will not give too much more than a quarter of size moon. So it's not a lot of material in there. But characteristics of these planets, the planets that are terrestrial. First of all, I would like to show you attention here for the density, right there. So the density is a measure of the content of that object, which means you take an envelope and then in one envelope, in fact, two envelopes, in one envelope you put nothing inside. And then you measure the mass of that object, of that envelope, and then you have the volume, right? And then you divide the mass by the volume and you have the density of it. Now you take another envelope and then you put a lot of iron bits inside. Now the volume, if you kind of blow both envelopes, and make them kind of blow inside. So the envelope that is filled with iron bits will be heavier than the one that is just blow with air, although the volume is the same. So density is basically a ratio between the mass and the volume. So if the volume is the same, but the mass is bigger in the envelope with iron bits, then the density of this envelope is going to be bigger too. So when you look at the planets and you use Newton's law to measure the density of these planets, you find that Mercury, Venus, Earth, and not so much Mars and Moon, look at this, Mars and Moons have less density than Mercury, Venus, and Earth. In fact, Earth is the one with the highest density. So this indicates that these terrestrial planets closer to the Sun, they have a higher content of iron in it. And this iron happens to be all concentrated in the center part. So if you take the planet per volume, the mass of it is relatively bigger, which means you have more iron content. And if you compare with the density of Jovian planets, as we will show next week, the density of Jovian planets resemble the density of water. In the case Saturn is even less dense than water. So if you could find a world that is bigger than Saturn, all made of water, Saturn would float on it. Now, since these terrestrial planets have solid surface or solid crust, from about 4.4 billion years since right after the formation of our solar system, all the way to about 3.2 billion years. So all these uh, planets and planetesimals, they were surrounded by rocky debris, by smaller objects, by meteoroids. And these meteoroids, because of the gravitational attraction of these early planets, they produced what we call the bombardment era. It was an era in our solar system formation in which lots of debris were falling down on all these major planets. Which means if the planet had no other means to resurface its crust, if there was no other means to redo its surface, either with with tectonism, we are going to see that, or oops, go back, either with tectonism or as a result of the hydrological cycle, which means our planet has water. Water in the oceans evaporates and then falls in the continent. And then this water in the continents finds its way to the ocean again. But in the process of going back to the ocean, it produces erosion and chemical weathering of rockies on the continental crust. And as a result, uh, the surface is always being redone as a result of hydrological cycle. So tectonism is one of the main factors resurfacing and changing Earth landscape. The second one is erosion caused by hydrological cycle or by glacier motions or by rivers, and all of these external factors are powered by the energy provided by our star, by the sun. So these impact craters are pretty much one big uh, meteor that penetrates the atmosphere, and as it does, it reacts and burns and vaporizes part of it or totally in the atmosphere as a result of friction. But if some of the meteor find its way to hit the ground and then you collect that piece, we call it meteorite. Meteorite. So meteorite is a meteor that found its way to the ground, and then you can go there and collect it. So it's the craters, as you have seen before, they are all kind of circular in shape. So you don't have a crater in general that is oval like that. If you look at craters in the moon, they are all circular. Why is that? Why is circular? If you go to the beach, and if you throw, I'm gonna go back to my ice cream here. Excuse me. So if you go to the beach and you throw a rock on the sand, so chances are, if you throw with an angle, the rock is gonna form an oval type of crater. So, oh, you mentioned erosion. That's a good guess, but I'm gonna give you another one, and I need to provide that information for you. When when an impactor hits the ground, when a meteor hits the ground, the crater it's carved is about 10 times as big as the impactor itself. So if you have a crater of 10, 20 miles, chances are you had an impact that was caused by an impactor of 1 mile. So why is that? Well, the reason of this kind of a circular shape is due to the energy that is released when the impact occurs. So that energy spreads out in all directions. I don't know why this is happening. Uh, a series of three images. Say this. Yeah, I don't know why this keep it flashing, but let me go away from here. So see another example. This is in Mars. So in Mars, you have also this circular crater because energy, which is kinetic energy, spreads in all directions and carves out this nice spherical bowl. And um, and then later on, in the case of Mars, you can see around this crater the development of a surface feature that looks like water flowing or mud flow. And in fact, this is one of the classical pictures suggesting that Mars' subsurface region is either filled with water or, like Natasha's discussion that she presented to us, or it is pretty much water frozen, and we call that permafrost. So what did you say? Yeah. That's you got it. So when once the energy of the impact is released, those seismic waves fall and travel in all directions. Um, they all have their different speeds, but wave fronts they propagate in a spherical way, and that's why you have this spherical bowl, which does not resemble the shape of the impactor, but it resembles the shape and the morphology of the energy that has been released. Now, young craters, they have something interesting. Young craters, they have this central peak, and central peak is an indication of youth in planetology. Wait a second. You know what I'm eating? It's an ice cream that I got at Trader Joe today. It's a pumpkin ice cream. It's very good. It has this pumpkin flavor. It's delicious. It has a lot of sugar though, because it's very good. Everything that has sugar is good, but supposedly it's not good for you. So let's look at some features in this crater. So you have these little craters around. See this catena here, a bunch of craters in line. Um, I don't know the details of it, but this series of craters could be the result of what's called secondary craters. When the impact occurs, some of this debris splashes away, forming this ejecta blanket you can see around here. All these kind of arrays is part of the ejecta blanket, and you have this kind of a rays streaming out. But also could be that once this impact happened, especially if this is a crater in the moon, um, and if that happened when the moon was still with pockets of melted material underneath, so this impact might have fractured the floor, allowing that some of the magma found its way to the surface. And so it was not uncommon to find tunnels of lava flow near these craters, especially those that have their basin filled with lava flow. And as this happens, this central peak goes away because get buried, in fact, get floated by lava flow. So some craters, let me see if I have pictures here on the moon surface. They don't have, oh, right there. See this crater right here? So it's all filled with lava. The central peak is gone. So it's like a lava went in it and then filled it completely. Now this has a little peak in there, as this one and as this one. So the lava was not able to completely fill that up, which also indicates these craters as being relatively younger than this one. So also terraces are these layers of um, around the craters that indicates how the material collapsed in the rims of the crater. So as I was mentioning, these lava tubes next that runs underground and next to the craters, sometimes they collapse, and as they collapse, they form this chain of craters. It's not craters resulting from impact, but from collapsing lava tubes. Um, so, how can we date lunar material? Well, you can either bring rocks from the moon to Earth, and then you can use radiometric techniques to date them, or you, like in an older technique, you would count the number of craters per surface area, and then regions that are relatively smooth, like this one. It's much younger than this one because it has more craters uh, per unit of area, and they are much more younger than this region here, where the crowding of craters is much more robust. So there are erosion going on in the moon, although the moon has no atmosphere or water. And this erosion is not because of wind, but because of impacts. So these impacts vaporize material, and this material eventually settle down. So this dust eventually settle down because of gravity, and as it does, it smooth out impact regions. I don't know why I keep having that. Okay. Now, Earth interior. How do we know about Earth interior? We know about the Earth interior because of earthquakes and because of the in the post-war, several countries engaged themselves in exploding nuclear bombs, and and then you have the Cold War going on. But the main result was you have enough propagation of seismic waves as a result of these explosions going on through Earth interior and being captured in seismic stations. So when you go to the dentist doesn't open your mouth and start cutting open your tooth to find out if there is a problem in there. What he or she does is to send out an X-rays, and the X-rays is like the seismic waves prospecting and trying to find what Earth hides within. So the same way, the dentist send the X-rays, and the X-rays interacts with your tooth material, and then that information is captured in a plate, and then the dentist can read out and find out what's going on, and decide to cut open or not. Um, so geologists they kind of do the same. They have seismic stations all over the planet, and every time an earthquake is set in any region on Earth, so waves propagate through Earth interior. It goes all the way to the Earth interior, and as it does, it interacts with the asthenosphere, with the Earth crust first, and then the lithosphere, the asthenosphere, the mantle, and then interacts also with Earth core. So how do we know Earth has a core that is solid in the inner part and liquid in the outer part? Is because of seismic waves. So differentiation, I just jumped a very important word in this chapter. Differentiation, or sometimes called chemical differentiation, is a very common phenomenon that occurs in the solar system once the object is completely melted as a result of heat. So differentiation is, or the object is a gas, like in the sun. So differentiation is the process by which a heavier material sinks down to the center of the planet or center of the satellite, forming a denser nucleus. is the idea. I saw in a book a very good example. Since I'm having ice cream now, I think I'm gonna get the last bite now. Um, when you imagine you go to the store and then you buy a bucket of chocolate chocolate chips vanilla ice cream, which is very good, by the way. And then you are crazy to get home and just enjoy yourself and the ice cream. But then as you park, your neighbor that you love so much come talk to you and keep talking to you and talking and talking and talking, and you get anxious because the ice cream is there. And then 30 minutes later, and this is in the middle of summer, you get to the kitchen, open the bucket, and then what happened? Your ice cream is all melted. So here's the question: what's going to happen with the chocolate chips once the bucket is entirely melted? So Earth gravity is going to bring all these chocolate chips down to the bottom of the bucket, right? And is going to cause a chemical differentiation. So you originally you had a bucket with chocolate chips kind of uniformly distributed all over the ice cream. But once the ice cream melted, now the chocolate chips is all there. It's called differentiation. The heavy goes to the bottom part. Okay. So chemical differentiation. Sometimes you read, oh, astronomers are trying to find if object A or B is differentiated, which means if it has a core that is relatively heavier than or denser, better saying, than the surface. Like the moon is the density of the moon is low, is small compared with Earth. So it means the moon is differentiated, but it has a very small iron core. So tides are important. We have high tide, low tides. Because Earth rotates, the bulging water, as you can see right here, because Earth rotates, the bulging water is going to be off a certain amount of angle in respect to the moon. So the moon pulls the water towards it, and as a result, the water that is in the other side of Earth stays behind. So you have two high tides as Earth rotates around its axis. So, excuse me, if you are somebody here with a little hat, right? As Earth rotates and takes you around, takes you around, takes you around. I don't know why I'm having this. Oh, I really don't like this. I have to find a better way to use this marker. So as it goes around, so you find a high tide here, and then you're going to meet another high tide in there because Earth rotates, right? So you have two high tides during a period of 24 hours. Now, Earth rotates, and because of friction, it drags this bulging water to an angle, but the moon brings it back. Brings it back. So this bulging water stays always in a fixed position in respect to the moon. And then we experience twice a day a high tide. Okay. Let's see what else. Magnetism. Magnetism is caused by alignment of the electronic cloud inside ions. So, for instance, ions, the atoms, they have, let's take for example, a hydrogen atom that has a proton and has an electron going around, like there. It's an electron and a proton, okay? And the electron orbit the nucleus. And this is not a good example of an atomic model, but it's the simplest one I can get now. Now, as a result of this, you have a charge that circulates around a center part. And according to what we learn in magnetism, this circulating charge, so if you have a positive charge that moves, This positive charge generates a magnetic field, generates magnetic field. So if you imagine Earth rotates in a period of 24 hours like this, right? And based on the fact that Earth interior is hot, so you have ions in there, ionized material, then these ions, as they circulate, they will generate this global magnetic field. So Earth has magnetic field and has liquid core as a result of that, because to have um, free, freely moving ions, you gotta have the material in the liquid form. So Jupiter has a magnificent magnetic field, strong magnetic field, because it is primarily liquid. Um, Metallic hydrogen is liquid, and then that is responsible for generating a global magnetic field. So Mars, Mercury, Moon, they don't have a robust magnetic fields, and we suspect because their core is not melted.